Okay, so far we've done Coulomb's law, and we've looked at the force between 2 point charges, and then we've said is K Q1 Q2 over R squared. And we said that looks a lot like gravitation, this attractive force that's proportional to 1 over R squared. But for electrostatics, this guy can be both attractive and repulsive. So now what I'd like to do is I'd like to take this force, and I would like to look at the potential energy in an electrostatic situation. Okay, so we know a couple of things. We know that an electric field, just like a gravitational field, would be a conservative force. So for example, if you release a charge in an electric field, then if you release it from rest, for example, then it will lose potential energy. And it's going to lose that potential energy at a cost to kinetic energy, right? So in an electric field, if you release a charge or you release something, we know just like in a gravitational field that potential energy and kinetic energy can pass back and forth in the field. And this is a conservative force. And through the work kinetic energy formula, we know this guy, that work is changing kinetic energy, but that kinetic energy is going to come at a cost to potential energy in this conservative field. We also know that work is F dot dx, or for example, for a dynamic force, a force that's changing with respect to position, we had to do a little bit of calculus, and this was F dot dr. Okay, so what I'm going to do then is, again, with work kinetic energy theorem for conservative forces, I'm going to instead choose to look at potential energy, because that's a lot more useful to us in terms of predicting the motion of the particles. So really quickly, let's look at minus delta U, the change in potential energy, is equal to the integral of F dot dr. Okay, so what I'd really like to do with this is, honestly, I'd like to come up with an equation for the potential energy at one single position. The potential energy at one single position. But if I'm looking at this equation, instead of getting the potential energy at one single position, I'm getting a change in potential energy. If I move the particle from one point to another, how much has the potential energy changed? And that's not an expression for an individual, one specific point potential energy. So what I'm going to do is I'm going to do a little trick here, and that is if I write delta U as final minus initial, okay, final minus initial is equal to the integral of F dot dr. Well, you'll notice that I haven't put any integration bounds yet. I haven't identified these two positions. What I'm going to do, the little trick that I'm going to do, is I'm going to say, what if this particle that I'm moving from one position to another, what if its initial position is infinity? What if it is infinitely far away in its initial position? Well, in an electric field, if you're infinitely far away from any of the other charges, well, then you actually have no potential energy, right? Just like we had no potential energy for a mass that is infinitely far away from any other masses. If it's not going to feel the field of any other mass, then it doesn't have the potential to do anything. So now I can take this delta U and I can actually write it as minus the final potential energy. So I'm taking this particle from really far off and I'm bringing it to this position right here, and I want to know just how much potential energy it has at a certain position. Instead of being a delta U, if I call the initial position infinity, where it has no potential energy, then I can now look at the potential energy at a single position. And this would be equal to the integral of F dot dr. And now I can put integration bounds here. It says that I'm bringing this particle through the electric field from an infinitely far away position to some position R. Okay, so we're going to find the potential energy at this final resting position in this electric field. So what I'd like to do then is the integral of F dot dr, but let's assume that the charge that I'm bringing in, I'm bringing it into the field from another point charge, we'll say. So that means that I'm using Coulomb's law for the force here, just K Q1 Q2 over R. So what I want to express here is I'll say that Q2 is the charge that I'm bringing in, okay? And Q1 is the charge that already existed. This is the charge that created the field, okay? So what I'm doing is I'm trying to bring in a charge Q2 into a field that Q1 created, and I apologize here for Coulomb's law, it's KQ1 Q2 over R squared. So we have the force dot dr minus UF, minus the final potential energy. And we can go ahead and do this integral. I'll write it out a little bit more suggestively, and that is KQ1 Q2 integral from infinity to R of R to the negative 2, right? That 1 over R squared is R to the negative 2, and that makes this integral pretty simple. So minus UF is equal to K Q1 Q2. R to the negative 2, I'm going to add 1 to the exponent. I get R to the negative 1, and I'm going to divide by that exponent, so I get a negative out in front, and then that's going to be R to the negative first, or 1 over R, evaluated from infinity to R. Okay? Great. When I place R in here, it just becomes minus KQ1 Q2 over R. When I put infinity in the denominator, a very, very large denominator is going to make that essentially 0. So I get minus UF is equal to minus K Q1 Q2 over R. The minus on both sides is going to cancel, so I say UF is equal to K Q1 Q2 over R. Okay? So the final potential energy, or the potential energy of a charge placed in the field due to another charge, is K Q1 Q2 over R. That looks incredibly similar to what we used for gravitational potential energy, which was G M1 M2 over R. But if you remember correctly, we had a minus in gravity because we said it had to be attractive, and that the potential energy of this system had to look like this in a U graph, right? We knew that at infinity, the potential energy had to be 0, but we also knew that if we place a mass in this gravitational field, we knew that it was going to be attractive. It was always going to move towards the other mass. Well, let's think about what Q1 and Q2 would do. If Q1 and Q2 are the same charge, they're both positive or both negative, well, this isn't going to be an attractive force. This is going to be a repulsive force, so I'd have no problem taking that 1 over R functionality and actually writing it as a positive here, which we got from the integral, meaning potential energy as a function of R, the distance between the two charges, would look like this, right? It's proportional to 1 over R, and it would make sense that if Q1 is a positive charge and I place Q2 in that field, we know that naturally, due to this electric field, Q2 would leave. It would go further away from charge Q1. Okay, but I've also wrote this potential energy kind of suggestively by separating the Q1 and the Q2. I want to highlight this term in front, this K Q1 over R, and this is actually what we call electric potential. Electric potential, okay, and that is V, electric potential V, and it has, well, if this is energy and Q2 is Coulomb or charge, then this guy electric potential would have the units of a joule per Coulomb. Okay? The electric potential that existed in the space of the field created by charge Q1 is equivalent to how much energy or potential energy will a charge receive in this space. Okay, so I want you to think about it this way. When charge Q1 was in space, an electric potential and an electric field existed all around that charge, but Q2 wasn't there yet. So there was no force and there was no potential energy of this system. Q1 existed in its own field. It didn't feel anybody else. There's no potential energy and there's no force. Okay? So anywhere in this space, let's call this point P, that space had an electric potential, V, of KQ over R. And it says that for every coulomb of charge that I place in this space, this is how much potential energy that coulomb is going to pick up. So when I placed Q2 in that space, the energy of this new system is now Q2 times the electric potential due to charge 1. So that's electric potential. What you're probably more familiar with is change in electric potential. In moving from one position to another, this is the more familiar voltage. So you've probably used that word before. The idea is that the difference between two positions in space, if they have a different electric potential, meaning one has maybe a higher percentage of positive charges, so it has a higher electric potential. Maybe one area has a higher percentage of negative charges, it has a lower electric potential. The difference between those two positions in space is what would drive motion of charges and what would drive electricity or the current to flow between charges. Okay, we'll elaborate on that a little bit more in the next video. But this is probably good for now. Electric potential and electric potential energy derived from the force, the Coulomb force between 2 point charges.